So I would like to welcome Dr. Achim Ahrens. Achim is a senior data scientist at the Public Policy Group at ETH Zurich and the Immigration Policy Lab, a joint collaboration with ETH and Stanford. Previously, he was a postdoctoral researcher at the Economic and Social Research Institute in Dublin, Ireland, and he holds a PhD in economics from the Heriot-Watt University. Welcome, Achim.
Thank you. Let me first see if that, how this works. Okay, fair enough. So first of all, thanks for inviting me. Thanks for assist to organize this. I'm quite happy that because I annoy them with plenty of emails and that they still invite me despite of that. So today I want to talk about machine learning. So I can say right away I'm an economist by background, and I want to talk a bit about sort of how machine learning is used by myself and by my group, and how generally machine learning is used in economics and social sciences. And I will talk a bit about software development as well. Yeah. So yeah, you already said it. So I'm a data scientist at the Public Policy Group at the ETH Zurich, which is sort of a joint lab with the Immigration Policy Lab. So it's one lab in a double role, so to speak, and we collaborate with Stanford as well, where we have a branch. And yeah, so I said this by my background is in economics and econometrics, so much of this machine learning today went way above my head. But still my tasks sort of in the group are sort of data science, econometrics, statistical support, and also sort of I've got my own research projects. And part of my role as well, or my sort of almost my hobby, is to develop statistical software packages. And I'll talk a bit about sort of the challenges that I face when doing that, and sort of I'll talk a bit about that as well. Yeah, so I said this already. So we're Public Policy Group and Immigration Policy Lab. We do policy evaluation with a focus on immigration topics. And in doing that, sort of we combine survey and registry data, so administrative data resources that often we get sort of from governments and statistical offices. And in terms of methodology, we use machine learning, but our main focus, so to speak, is causal inference. And so part of my talk as well is about how to combine causal inference and machine learning. Just to give a few sort of recent examples, projects from our lab is, in my group, we had recent projects on counter-speech strategies for hate speech, discrimination on online recruitment platforms. We'll talk about that a little bit, and the effect of citizenship on immigration, on integration for immigrants. So yeah, I'll talk about the increasing importance of machine learning in economics and social sciences. I talk about how machine learning and causal inference can be combined. So how can you actually use machine learning to facilitate causal inference? And I talk about the challenges of writing accessible software for non-machine learning experts. So yeah, in recent years, machine learning has increasingly been leveraged in social science and economics. I mean, natural language processing is for sure one big topic. And often machine learning tools can be sort of used off the shelf for policy questions. For example, one issue would be, say, predicting long-term unemployment. So at the moment, some person starts to be unemployed. In the context of active labor market policies, employment centers might want to know, is there a risk for that particular person to be long-term unemployed, so that we maybe target that person differently. Another example might be in the judicial context. You might want to know whether if someone commits a crime, and whether you put that person right away in prison, or if you can let that person go out on bail. So that we sort of predictive policy questions where you can use sort of the standard machine learning toolbox to do prediction. But most often in our context, the research question is of causal nature. Example would be, say you want to predict hotel occupancy rates. A high price would predict high hotel occupancy rates, but that doesn't mean that the hotel owner should increase prices to increase occupancy. So that's sort of where you need to think a bit deeper. So that's just like a really fundamental example, yeah. So typical research question in the work I'm doing and we are doing at the lab is, so what's the effect of policy X on outcome Y, yeah? So that could be the effect of refugee policies on long-term labor market integration. So we are looking, for example, in a few projects in Switzerland. There are a couple of policies that govern whether refugees are allowed to work, how long they are allowed, or starting sort of, when they arrive in Switzerland, they are not allowed to work for a couple of months, and the length of that affects sort of the long-term employment. They are, for example, not allowed to work in certain sectors in specific countries. So we look at all these effects of this on long-term labor market outcomes. Another question, as I mentioned earlier, the effect of citizenship on wages and employment. So actually the fact that if someone has been living here in Switzerland for many years, where they're sort of actually having citizenship, and it facilitates also the integration and labor market outcomes after that. So the math toolbox is quite different from the machine learning toolbox. So what's been used is a lot of quasi-experiments, difference and difference analysis, regression discontinuity design, instrumental variables. So that's a set of, I can't obviously explain all of these methods, but a set of methods which are all focusing on finding identification strategies that give us sort of a causal treatment effect. Yeah? And allow us to say, well, this policy affects for that specific group, long-term employment or income and wages by so and so much. That this sort of set of methods often described as the credibility revolution, there's famously a book from Ahrens and Pischke, Mostly Harmless Econometrics, which sort of summarizes all of this, and a recent Nobel Prize also went to sort of this whole idea of using more targeted identification strategy for causal inference. To give one example, in February 2014, there was a referendum in Switzerland where Swiss voters voted against sort of the idea of mass immigration, and what Switzerland, or the Swiss parliament, did in the following was to introduce a set of policies which affected occupations with an unemployment rate above 8%. And these policies aimed at improving the hiring of the domestic workforce, so of Swiss residents, relative to outside workers. So the idea being, we rather, making it easier for a Swiss resident to be hired compared to someone, coming from outside. Concerns there were, simple idea would be just like to look at sort of immigration before and after this policy was introduced. But there are, we're working with observational data. Their labor market outcomes and immigration is confounded by seasonal and business cycle effects. So just doing sort of a before and after comparison will often not give you really a causal effect. So what we've done there in this context, we use two methods. I just go really roughly about this: regression discontinuity design and difference in differences. On the left side is essentially the idea we are plotting immigration as a function of unemployment rate, and the policy, as I said, so it's targeted, so it's defined based on the unemployment rate. So if there was an effect of this policy, we would see a threshold at this 8%. We would see an effect at this 8% threshold. Yeah. So the causal identification really comes from comparing, so I can show it here, from comparing occupations around this threshold. The idea being so that this threshold, whether it's at 7 or 10%, it was done by the policymaker, but it's as good as random. Excuse me, yeah. And on the right side there is the a difference in difference approach. The idea being, I said earlier, one concern is that we have business cycle effects. So what we're doing, we're comparing occupations just above and just below that threshold, and we assume that the trend sort of is the same because they are affected by the business cycle in the same way. So we get sort of an imputed counterfactual, which gives us the effect size. Yeah. In the end, so that sound all quite nice. In the end, it was all much more boring. And what we found actually in this project is that there wasn't much of an effect at all of this policy, and that was really what we went back to the policymakers and saying, okay, actually, your sort of these prioritization policies, they didn't do much actually. All right. So this was really just an example from the classical sort of economic toolbox. Generally, so I'm comparing this now to machine learning. So supervised machine learning generally focus on prediction classification tasks rather than causal inference. You know this all better than me, so there's a large toolbox, regularized regression, random forest, support vector machines, neural nets, etc., etc. But all these are sort of, prediction focused, right? So typically procedure is algorithms trained on some data and we validate it on unseen data. Yeah, so the strengths really what I as an economist see there is this strengths of out-of-sample prediction, out-of-sample classification, work with high-dimensional data, and data-driven model selection, which I think is an important point. So question, so how can I leverage these methods in a causal context? And there are at least three common approaches. One is that, machine learning can make it much easier to deal with treatment effect heterogeneity. So I've talked about sort of a treatment effect, but the treatment effect could be very different for different kinds of people, say young versus old people, male versus female, etc., etc. Finding out about this treatment effect heterogeneity is something where we can use machine learning. There is, for example, the work from Susan Athey at Stanford on causal forest. Causal forest is a bit like a random forest, but when you grow your tree, instead of you do your splits to based on the estimations of treatment effects rather than on the variation. Another fascinating field is policy learning, where we are not just asking what's the treatment effect, but we are asking who should become which treatment. So we are using that, for example, in the context of citizenship, where we send, so there are eligible immigrants in Switzerland, people who usually have lived more than 10 years in Switzerland, and we are sending letters to them, letters with different types of wording. And the question is who should become which letter? And given that there's a heterogeneous immigrant population in Switzerland, we can sort of, based on language, based on sort of immigration background, we can sort of try to figure out which treatment is best for a certain group. And the third point is robust causal inference in the presence of high-dimensional controls and instruments. That's something I want to talk a bit more about, because that's something where I've contributed a little bit in terms of software. So I really try to boil this down to the absolute simple minimum, but I want you to think about this. So I earlier gave some examples of causal identification strategies. You can essentially use this idea that I'm sort of now presenting in the context of these causal examples of these causal identification strategies. So the idea is we have some outcome, we have a causal part, which is our treatment, and it's a policy variable, and we have a treatment effect theta, and then we have something else, which is like X, our controls. And we have to control for them, but the question is, how do we want to do that? And only if we control for them, we really get our causal effect. An example, an application also from colleagues in my lab would be assessing hiring discrimination on a job platform in Switzerland as well. So Y would be a contact rate, D a minority indicator, say whether someone has an immigration background, and X are job seeker characteristics. So we now essentially want to know whether contact rate, so the probability that a person is being contacted is affected by the immigration background or ethnic background. Obviously, we have to account for the job seeker characteristics, because they are seen by the hiring person, so we need to control for them. So we can only interpret the discrimination effect theta as causal if we control for our axis. So how we control for axis? Well, in a standard, like traditional context, we would just use ordinary least squares. Yeah, very simple. We just assume linearity. That's it. Well, that has some problems. Well, the Nuisance function or the x might enter in a sort of nonlinear way. There might be interaction effects. We might also have, as in this example, a lot of high-dimensional, like many controls. Yeah, there might also be text data. Text. Part of the data might involve text, etc. So it's often much more complicated. So we don't know which controls to include, and we don't know how to include these controls. And so the solution to this is double machine learning. And the idea is incredibly simple, but it's very general. So the idea, essentially, we fit a machine learner of y against x, and you fit a machine learner of d against x. And our actual causal model, we estimate sort of with the residuals, so to speak. There are two flavors of this traditionally. So the first generation was just applying this to using the lasso for this, because the lasso is a method where the theory is very well developed. But using sample splitting, you can essentially use like any machine learner to this. Why do we need sample splitting? Because otherwise we would have overfitting issues very quickly that then would sort of invalidate our causal inference. And the approach is like very, very, very general. So it's just like I've used this simple partial linear model, but it could be a much more complicated model. This is actually what came out here. So this is sort of the effects of the hiring discrimination, and we see that depending on the immigrant and minority background, there is a hiring discrimination between 4 and 19%. So these double ML approaches are increasingly being used and as a central identification strategy, as a robustness check, and they also being used in RCTs because they actually give you a little bit more precision. Yeah. So even if you don't really strictly have to use them, they can give you more precision. So examples which is like they were used in COVID, like in some of the COVID studies for studying health or development, health outcomes or in development programs. So my point is that the adoption of these machine learning and double machine learning methods is partially still being hindered by lack of knowledge and also partially being hindered by availability of software. So these double machine learning approaches have been implemented in R and Python. There's a program called Double ML, and there's also one called Econ ML, which is by Microsoft. Now, lots of the economists and social scientists use Stata. Maybe no one here knows Stata, but Stata is quite a widely used software with a focus on causal inference, and only recently they added some machine learning stuff. So I took it with two co-authors, one of which is a theorist who sort of developed these methods. We took it up sort of to develop some of the software to make it easy and more accessible for economists and social scientists to use these software. Yeah. So example user often, so we are like World Bank and IMF, so that would be like as international organizations, as academics, so they often, many of these, the researchers there use data. All right, so we've developed some software in this context, so for also implementing sort of double lasso and double ML approaches. And, oh yeah, I said this already, so there's similar software for R and Python in this context. And what we found sort of when sort of making the software, which is obviously free and everyone can use it, is so it highlighted some risk because we are getting questions. So how am I supposed to use this? Does it make sense to use it for my application, et cetera, et cetera? So one of the issues we found, so people usually many researchers and users often focus on a single method. They don't spend much time on tuning. Often the lasso is being used because that's sort of like the novel thing in economics. No or insufficient tuning. And we also found just out of the machine learning context of whatever the default is has such a huge effect on what people end up doing later. So we are writing very extensive help files and tutorials and everything. But still people just go with the default. And so we are spending a lot of time on simulations as well and going through examples to actually justify the defaults we are using. So one of the issues was like, we need to get people to use consider a more, wide set of machine learners. So what should be the default method? And one of the what we came up with was to basically, there's no novelty here, but just to nudge people into using a different thing is to propose to use stacking regression more. So the idea being we nudge people to don't just use the lasso, don't just use boosting, just take a wide set of methods, put it into your stacking algorithm, and you can use that together with double device machine learning or double machine learning. We have also done some simulation experiments to sort of make this point more clear. We've generated some very simple data. It's like sort of a calibrated simulation based on real data, but we've we then sort of consider two data generating processes where one is totally linear, the other is more non-linear, and we are trying to show, or we showed here, that using sort of traditional, this goes back to my very start, just using OLS, performs equally well to stacking here at the very bottom, but that obviously only if the data generation process is linear. But the point is, if it's more complex, quickly stacking will do much better, and that's really what people should use. So that's sort of simple simulation that just, so we can go to users and say, guys, consider more than just, consider a wide set of machine learners to do actually your causal effect estimations. Yeah, that was it. So really, summary of what was I saying today? Machine learning is sort of getting more and more common in economics and social sciences. Really, when I did my master, like there was no machine learning. Now it's really part of the syllabus. And machine learning often cannot be used so just like off the shelf, but because we are often looking at causal questions, but it still can help. And double machine learning is one of the examples. Other examples, heterogeneous treatment effects, policy learning, which I didn't really talk much about today. Yeah, thank you.
Thank you, Achim, for this very nice presentation, and especially telling us about this concept of double ML. So it was very interesting. We are running a little bit late, so we have time for maybe one question.
Just a very short question. Is double ML related to structural equation modeling?
Sort of. Related, yeah, related. Related in a vague sense. You can use double machine learning together with structural equation modeling. So I think that's the way to think about it. So the idea with double machine learning is you have a model, right? So that tells us, how, y and x and d or whatever are related to each other. And then you have some other stuff. And taking care of that other stuff, that's what double ML does. And structural equation modeling would just sort of stop and just, you would have to say how your other stuff is related to your variables of interest. So related, yeah, no, but yeah.
So thank you again, Achim.
Yeah, thanks.